Sorry, I ran into a couple difficulties, so now I'm going to continue the lecture. Sorry that's going to be such a short video. The point is, we just showed via a rather long argument how to count the number of subsets of a finite set using induction. And the point is you split it into two kinds of subsets. Okay. Now let's do a much shorter proof using our counting argument. So show that the number of subsets of a finite set A is 2 to the cardinality of A. Here this should be the cardinality of the power set of A, right? Okay. Now for a counting argument. The idea is, since A is finite, we can list the elements of A in a sequence. Since A is finite, write A is equal to A1, A2, all the way up to AN. And now, to build a subset, essentially you make A sub n choices where at each stage you make the choice about is AN inside your subset or is AN outside of your subset. You can also think of this as making a string of zeros and ones, where a 0 in that place means you don't include that element in the subset, and a 1 means you do include that subset. So the string 0, 0, 0, 0, 0, or all zeros would correspond to the empty set, because nothing is included, and the string 1, 1, 1, 1, 1, all ones, would correspond to the entire set A, because every element is included. Anyways, to build a subset, we make A sub n choices, and each choice has two options. By the product rule, we're making one of two choices A to the n times. Well, n times. Sorry, n choices, because there's 1 through n. So 2 to the n choices, or 2 to the n configurations are possible. So if the cardinality of A is equal to n, because there are n elements, then there are 2 to the n subsets. So in this case, the combinatorial argument is much faster than the induction proof. Okay. So that's a bunch of examples of just the product rule on its own. Now let's do the sum rule. This one seems even more simple. If a task can be done in n1 ways, or n2 ways, and n1 and n2 are distinct, then the task can be done in n1 plus n2 ways. And maybe this seems a little foggy, but I think the examples will make it much clearer. So for instance, as a very basic example, a student can choose a project from 3 lists. First list has 13 projects. second has, I don't know, 8 projects, and the third has 11 projects. How many projects could the student possibly choose? And the answer is 13 plus 8 plus 11 possible projects. Right? We're not breaking this into you must do one from the first and one from the second and one from the third. It's you must do one from the first or one from the second or one from the third, and then you sum. If you had to do one from the first and one from the second and one from the third, then you'd multiply all these together. So it turns out that the sum rule can often be used in conjunction with the product rule. Let's see an example of that. So example, let's find the number of passwords where the length of the password is 6 through 8 characters. Each character is an uppercase letter or a digit. And all of the passwords must contain at least one digit. Okay, basically here, the first thing that we examine is that there are 3 choices for how you make your password. Either it's 6 characters long, or it's 7 characters long, or it's 8 characters long. It's not possible to be both, and there's no overlap. If your password is 6 letters long, or 6 characters long, it is not 7 characters long. So the total number that we're looking for is equal to the number of passwords with 6 characters plus the number of characters or passwords with 7 characters plus the number of passwords with 8 characters. This is the sum rule. And now we essentially break the problem into each of these 3 chunks. And now I want to find what is the size of passwords with 6 characters. Okay, well, let's think about this. If we forget the last condition, then it's just asking for 6 characters where each character is either an uppercase letter or a digit. So it looks like there are 36 possible options, and indeed this part looks exactly like finding the number of license plates. However, each password must contain at least one digit. So there are perhaps a number of ways of going about this. One way that would be exhausting in a very bad way is to count the number of passwords that have a digit in the first place, plus the number of passwords that have a digit in the second place, etc., etc., etc. But then you might have a lot of overlap, and you might be overcounting things, which is something that we're at a big danger of by doing that method. So the correct idea here is actually to find the total number of passwords equals total number of passwords on 6 characters. And then we could just subtract off the number of passwords that have no digits. And then what we'll be left with is the number of passwords that have at least one digit somewhere. So we already know what the total number of passwords is, right? The total number of passwords is going to be 36 to the 6th because we have 6 slots, and in each slot we're going to put either a letter or a number. And then the number of passwords with no digits means I'm looking at the number of passwords that I can create only with letters. So minus 26 to the sixth, right? I have 6 slots, and in each I'm just putting a letter. So the number of passwords with 6 characters, such that at least one of the characters is a digit, is going to be 36 to the sixth minus 26 to the sixth. It's the same story for P7. This is going to be equal to 36 to the seventh minus 26 to the seventh, and then size of P8, I should put sizes here. Size of P8 is going to be equal to 36 to the eighth minus 26 to the eighth, because I have a password that is 8 characters long, and what I'm doing is I'm finding the number of passwords 8 characters long that contains at least 1 digit by taking all of them and subtracting off the number that contain no digits. So everything that's left must contain at least 1 digit. And thus I get that the total number of such passwords is equal to 36 to the sixth plus 36 to the seventh plus 36 to the eighth minus 26 to the sixth plus 26 to the seventh plus 26 to the eighth. And thus we find the total number of passwords. Here I'm using several techniques. First, we're using the sum rule to split it into the 3 different types where you do one of the 3. And then in each place we use the product rule to make each of these counts. This idea of subtracting off the things that you don't want, and that being easier than finding all the different possible cases, is one that will come up a lot. Okay, let's do another example, or another rule. So the subtraction rule. And this is essentially the inclusion or exclusion principle. So if a task can be done n1 or n2 ways with overlap between the n1 and n2 ways, then the number of ways is n1 plus n2 minus the size of n1 intersects n2. Here this is kind of sloppy language, but I'm considering the n1 ways. N1 here stands either for a set or the cardinality of the set. Here I'm using kind of set notation. This is kind of bad. But essentially what this is doing is the inclusion-exclusion principle, which is saying that if I want the set of A1 union A2, this is precisely going to be the cardinality of A1 plus the cardinality of A2 minus the cardinality of the intersection, A1 intersect A2. Right, so you have n1 ways or n2 ways, but there's some overlap between the n1 ways and the n2 ways. You have to subtract off the number of ways in which they're the same. Okay, let's do some more examples of this counting. So for instance, let's think about 5-element DNA sequences. So DNA sequences consist of 4 possible letters. A for adenine, G for guanine, T for thiamine, and C for cytosine. Probably I should have done them A, C, G, T, but whatever. I remember that from my high school biology class. Go me. So let's find the number of 5-element DNA sequences with a certain number of conditions. How many 5-element DNA sequences contain or do not contain C? Okay, well, the condition of not containing C, this kind of brings us back to the subtraction stuff. So the number of sequences which do not contain C are equal to the total number of, oh wait, not containing C means that you only have A, G, and T to play with, right? Because if C appeared somewhere, then you wouldn't be in here. So essentially, this is 5 slots, and in each slot you can put either an A, G, or a T. So this is just 3 to the 5th. You have 5 choices to make, and in each choice you have, or in each slot you have 3 choices. So 3 times 3 times 3 times 3 times 3 is 3 to the 5th. Now let's look at how many 5-element DNA sequences do contain C. So once again here, if I want to find all of the sequences which do contain C, it's easier to find the number of all of the possible sequences and then subtract off those which do not contain C. And I'll be left with the number of those that do contain C. So again, I'm going to look at, this is equal to the number of all possible minus the number of sequences containing or not containing C. So in particular, this is going to be 4 to the 5th minus 3 to the 5th, similar to the last problem that we did. But now there's one more interesting one. Let's find the number of 5-term DNA sequences which start with T or end with G. Okay, so the number that start with T is pretty easy to count because we're going to have a T blank 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 blank. And so there are 4 choices, or 4 slots, and in each slot you have 4 choices. So the number that start with T is 4 to the 4. And ending with G is the same story. There's going to be a G here, and then you have 4 to the 4. Okay, but the issue is we're actually double counting here because in here we're counting all possible things that start with T. Well, some of the things that start with T also end with G and have some sequence in the middle. And they're also being counted over here because some of these sequences that end in G also start with a T. So in particular, for instance, this sequence T, A, G is counted once in here, in this 4 to the 4. It's also counted once here, T, A, G, right? So it's being doubly counted. And so to rectify this, I need to subtract off those things that are doubly counted. So the total number is equal to 4 to the 4 plus 4 to the 4 minus, and now I need to look at the size of the intersection. That's the size of, if you have a T first and then a G second, how many choices do you have? Well, you have 4 choices and 3 slots, so minus 4 cubed. So here, this number should be 4 to the 4th plus 4 to the 4th minus 4 cubed, where this is really just the inclusion-exclusion principle. My set A is the set starting with T, my set B is the set ending with G, and then if I want to find the cardinality of their union, I do the cardinality of A plus the cardinality of B minus the cardinality of their intersection, which are 5-element DNA sequences starting with T and ending with G. Okay, so those are some, technically those problems are all accessible once you know the inclusion-exclusion principle from set theory and you know about the cardinality of products of sets. That's all the product rule is really saying. But now we can kind of apply them to some interesting combinatorial problems. We'll do some more interesting combinatorial problems starting in the next lecture. And once again, sorry that this lecture was split up into 2. I had some issues with the computer. All right, see you in the next lecture.